Action.
All right. Thank you, Paul, for this opportunity. So my name is Marouane Salhi. I'm the CEO and co-founder of Qubit Engineering, a quantum optimization company performing in the energy space, as you will see in my presentation. It's a pleasure to be presenting our vision and our work at Qubit Engineering. I'm a computational physicist, and I'm happy to answer any questions after this presentation. Uh, or reach out to me if you need to. Yes, let's get started. So the presentation is combinatorial quantum optimization, a reason to rethink our computational problem. So it's a very long title, but we mean to say this message. It's very important, and that's what I'm trying to convey through this presentation. Let me start by presenting some of the popular combinatorial optimization problems. They're known as the classical world, and I want to define what's a combinatorial optimization problem, and I'll slowly goes into the quantum aspects and why it's relevant and the use cases and so on. So I'm showing here the travel salesman, the job scheduling, the knapsack. We can add what Elia, she did a great presentation, by the way. Um, what you mentioned, like financial portfolio optimization, job scheduling, I'm showing here, and many other optimization problems or combinatorial optimization problems. What we look for in a combinatorial optimization problem is to find best solution out of finite number of possible solutions, where each solution is actually the combination of a subset of the total number of elements defining that problem. I will get a little bit more into. I'll try to explain myself a little bit more. But what we're trying to do is to find a solution that is a combination of an element of some elements, part of a bigger or larger element. The example of the portfolio optimization, for example, is to pick the best stocks that you want to invest in out of the many stocks available. The example of the travel salesman, the traveling salesman problem is the finding the best route to go through all cities in the shortest path possible. There are many ways to go through these different cities. The job scheduling or even the knapsack, they're all combinatorial optimization problem where we're trying to find one best solution that is a combination of the subset of the total elements that makes that. Now, let me just show you the only formula here in my presentation, which is a combination formula. It's mathematical expression to evaluate how many possibilities out of the sample of samples or of configuration out of that you would take from a bigger group or ensemble of elements. And let's think about it this way: if we have, let's say, if we have a number of guests, we call them R, and we have a number of seats. Let's say we have a fixed number of seats, 100, and we're trying to find out what is the number of possibilities we can distribute our guests on the seats, and you'll be surprised by the value. So if we, as I said, if we have 100 seats and we only have 5 guests, and we're trying to find how many different ways we can distribute our guests on these seats, we'll have more than 75 million possibilities. Now, if the number of guests is 25, it's going to 242 sextillion possibilities. So that's, I think it's e to the 21 or 22. If we have 50 guests, then it's over 100 septillion possibility solutions. This is just to emphasize on simple, small combinatorial optimization problem, which is the case of distributing our guests here in a room with 100 seats. How rich and how complex there are almost. It's a finite number, but it's huge. It's a number that we cannot cover through what we call the brute force. If we're trying to cover all possibilities, even using a supercomputer, it will take us an eternity to do that. My main message here, just think about the complexity or the richness of these combinatorial optimization. Now, let me jump into what we call combinatorial quantum. Combinatorial quantum optimization is simply the implementation of quantum computing technology to find the best solution in such problems. Why? Because quantum computers can leverage quantum effects to explore multiple solutions in parallel, basically navigating much faster this vast space of possible solutions. So the idea is that quantum computing can help us finding the best solution among this huge number much faster. And in fact, I want to relate to what Playa did in her first presentation. The idea is the following: is that we are tackling a problem very rich and very complex, but we think that, or we believe that, with a mature quantum technology, we can navigate this space and we can achieve results much faster or even not even accessible using classical computers or classical approaches. But we have to be realistic. And today's quantum computers are not there. They're not fully operational in the sense that first they need what we call error correction. They require error correction, and they have limited connectivity. And in fact, to say when I mention connectivity, we mean the connectivity between the qubits. The fundamental elements that makes a quantum computer is this quantum processor that we call qubit, and any quantum computer is defined by the number of qubits and about its connectivity, the connectivity between these qubits. And certainly, we don't have enough qubits at the moment. Any of the quantum computers available today. I should also mention that when we talk about optimization, in general, we talk about special type of quantum computers. And the main quantum one that is known has been in development by a Canadian company called D-Wave, which is a pioneer in that aspect of solving quantum optimization problems using the quantum annealing approach, D-Wave. But these limitations did not stop engineers and scientists from either the academia or the private sector to develop interesting new technologies, algorithms, and systems to solve these vast and rich combinatorial optimization problems. And I will show here a few companies, and I can just mention the momentum that is really going into developing machines and systems to solve, and I'm emphasizing on the fact of machines and even machines that are quantum machines and non-quantum machines to solve these combinatorial optimization problems. So the quantum machine here is represented by D-Wave in this example. The non-quantum machine, for example, is represented by Fujitsu. They have their digital annealer, but there are other examples of new machines and the new systems. The rest of the companies, they come under the umbrella of what we call quantum-inspired systems. Laia mentioned that. So these quantum-inspired systems is basically a solver that can tackle these combinatorial optimization problems, but using classical computing. And I think, I believe it's very important here to emphasize that one of the biggest inventions today of humankind is supercomputers. These are really, really sophisticated machines. They are the most developed technology. And what we need to make sure that the message that quantum computers will not replace regular computers or classical computers or high performance computers, but it will support it. And the idea of that we will have suddenly just throw away all of our classical computing technology out of the window. It's not true. It's not real. In fact, the way we look at things is that we're going towards what we call hybrid systems. That means we're combining the classical computer with the quantum computer. Just like Liam mentioned, their effort in building these quantum machine learning systems where they're trying to combine or replace some of the layers in their neural networks with some quantum components, and the rest is on classical. That's the way to go. Now, the other message here, as I want to emphasize here from this effort, is that these companies, they are all doing an effort and investing in solving combinatorial optimization problems. So the question is why and how did this even come? So first of all, I mean, the quantum computer, if you're trying to use a quantum computer, you cannot solve your problem, the computational problem that we have today in our industries, whatever industry it is. It's not immediately, this most of them, not immediately projectable to run on. You need to cast it in many cases into what we call combinatorial optimization problem, so you can take advantage of quantum technology. That means even before solving your problem, even before, we're not talking about the technology and quantum technology ready or not. The problem also needs to be ready. The problem also needs to be cast into a format that the quantum computer can digest and can solve. Um, and this is getting into this main point, and I think this slide is the core of my message today, is that converting an optimization problem into a meaningful combinatorial optimization problem is not always easy or possible, but it's not impossible either. And it is crucial for the development of any application or use case in the quantum space to go through this step and build an equivalent expression, an equivalent description of the original computational problem, forecasted into what we call combinatorial optimization. So there's a difference. You can have a computational problem that we use and solve on classical computers, to be able to go from that computational problem, that classical application, into using a quantum system or a quantum solver or a quantum inspired solver. You need to, for that conversion, you need to have this this description, this combinatorial optimization. And in fact, now the effort to build what we call a use case, a quantum use case, or a quantum use case, we need to have a collaboration. We need to have, basically a strong interaction between the companies that are building the hardware, that are building the system, and the companies who are developing the actual application. So they can make this happen. They can merge the algorithm and the software side of the application with the hardware or the system, the quantum system or the quantum inspired system. And indeed, this is exactly what we've been doing at Qubit Engineering since 2018. We've been developing quantum optimization formulation for the design of wind farm, for wind farm layouts, with the aim is to have more efficient wind farms and to decrease their cost. So we picked our first use case is designing more wind farms, and we've been developing this formulation to run on. We started on using T-Wave as a quantum machine, but then we also then we jumped on using quantum inspired systems by Microsoft and then other companies, other collaborators. And in fact, I mean, this is what I just emphasized through collaborations with these quantum computing and also uh, application leaders in the wind industry. We build a functional combinatorial optimization uh, formulation for the wind. And I need to emphasize on one thing. When you first think of the, the wind farm optimization problem, the first thing that comes to my mind is that we are solving the continuous fluid dynamics problem, and that's the problem. That's how we've been solving it for decades. Now to actually solve it using any of these quantum systems, whether a real hardware quantum annealing machine or using quantum-inspired systems, you need to convert this problem into a discrete combinatorial optimization, which is very different, very non-end. And this is the true for many other cases too. So as we said, it's not something that is straightforward, but it's not impossible either. And through our experience, the results of the outcome, once things are done properly, are amazing. In fact, we think that a significant degree of complexity is reduced when we do this conversion from a classical continuous problem into a discrete problem. And there is no loss of the richness of the problem, as some may speculate, may expect, because we're going from a continuous space to a discrete space. So the application that we developed is basically to design wind farms that can generate more. That means higher production, higher income for the developers, but also reduce their cost, their overall cost. And we are proud of this first application, and indeed we are commercializing it already. And what we are using, and I know I will get some of these questions in the chat later, maybe, is that how big the problem are you solving? If you want to use a quantum machine, let's say the quantum annealing machine, you are limited with the number of qubits that you have. If you are to use quantum-inspired systems, then the infrastructure or the hardware underneath the algorithm is classical system, and for that you can, in a reasonable way, you can scale up your system as much as you want to make it, I mean, as long as it is efficient and works. And that's why today we are able to use this combinatorial optimization approach for industrial scale problems, for real use cases, and generate results that are not just competitive, but outperform in many instances the classical approaches. We're still calling it, we're calling it a quantum inspired system. There could be a debate. It's not running on actual quantum hardware and all of that. We're not. We're totally aware of that, and we want to call things the way they are. But certainly this is a changing the way we think of our computational problems and the way we solve them. And in fact, we're not stopping there. We are looking at our next application, which is the optimization of the electric power grid. So, in fact, the electric power grid and the design of wind farms share a striking resemblance in the mathematical underpinning, or the way they're built mathematically, and that's why we believe that the electric power grid will be as successful as the wind farm design first use case. And we do have sponsors and collaborators for this new our second application. In fact, what we vision is that using this quantum formulation approach of formulating the different kind of problems, we can build an optimization system for the overall grid, what we call the smart grid. Basically, the ability to manage and optimize the whole energy infrastructure that is connecting wind farms to solar plants, maybe to nuclear plants, and to the actual electric power grid. And being able to do that today with systems that are quantum inspired systems. In the future, we may be running it on the quantum on an actual quantum computer or a quantum optimization system. So in terms of opportunity in the use case in this is create the ability to provide additional value, um, efficiency, something between 2 to 10% efficiency and cost reduction is huge on the market. I'm trying just to tell you to share the market opportunity for this and what kind of impact this technology and this vision changing how we solve computational problems can have on the market. So yeah, I'll just share that we Qubit we received uh, 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 support. We received a grant. So we're very proud to be the recipients of uh, and the participants at the Innovation Crossroad program by DOE at the Operational Laboratory to support us in the development of this approach and this technology of optimization for the power. Uh, I this kind of brings me to the end of my presentation. Thanks for your attention. I'm showing here my email if you would like to reach out to me, and I'm happy to answer any questions you may